So the topic of today's lecture will be Laplace transform. And Laplace transform is often used to analyze a circuit, but before we get into that, I would like to just give a small introduction on what is Laplace transform. So let's say we have some kind of a function f of t, and we want to express it in S domain. So in order to do that, we take Laplace transform denoted using letter S. What it means essentially is that we're taking the derivative from t equal to 0 to infinity, at the same time multiplying it by an Euler's number to the power of minus sst dt. So as a result, we get capital F of S. Here, an Euler's number to the power of minus s multiplied by t serves two distinct purposes. The first one, it makes the whole thing converge. And the second one is that it essentially describes the whole signal as a combination of some exponential behaviors. Okay. We may also take an inverse Laplace transform. So let's say if we have our function capital F of S, we can take an inverse of that one and get back our function f of t expressed in time domain. So please remember this set of rules, let's say Laplace transform pairs, that I've taken from the book on Introduction to Electrical Circuits Theory. This is essentially all that we need to analyze a circuit using Laplace transform. So I'd like to solve an example. So here we have to find a Laplace transform of the following function. So if we do that, we use our capital letter L. And please pay attention to this exponential. So first, let's use the property of a Laplace transform and write it this way. So we can take a Laplace transform of a constant separately from this whole big term. As a result, we can first consider, let's say, this part of our equation. Let's denote 1 plus 2t as f of t, okay? Then this whole thing becomes 5 multiplied by Laplace transform of Euler's number to the power of minus 2t multiplied by f of t. So then, if we look here, we may see that the resulting equation, so to say, will be 5 multiplied by f s plus 2. So what happened essentially is that it shifted in its s domain. We may call it as well a frequency shift. So if we were to take the Laplace transform of our initial function, we would get Laplace transform of 1 plus Laplace transform of 2t, which is equal to 1 over s plus 2 multiplied by 1 over s squared. So you may wonder, why am I writing 1 over s if Laplace transform of 1 is not written in this table? That is a fair question. So actually, whenever we see some kind of a function, let's say function 2t, it is actually 2t multiplied by step function. It is true for circuits in Laplace problems because we assume that our circuit started operating at time t equal to 0. So we start observing our circuit at this point, and what is u of t? It is essentially a step function that did a step, so to say, at time point t equal to 0. So it is usually always there. So whenever we write a constant, for example 5, our f of t is equal to 5, it actually means 5 multiplied by step function. So in this case, our 1 is essentially 1 multiplied by ut. And since the Laplace transform of ut is 1 over s, we write 1 over s. Okay, now that we took Laplace transform of the initial f of t, we have to see the contribution of this Euler's number to the power of minus 2t. So here, as we may see in our table, there is a special case for that. So whenever we see an Euler's number, we can confidently add the coefficient to the s. So in that case, our coefficient is minus 2. So what we can do is f s plus 2 is equal to 1 s plus 2 plus 2 multiplied by 1 s plus 2 square. As simple as that. We can further simplify it and get s plus 4 over s plus 2 square. So what we get is the Laplace transform of the initial function, let's call it capital F of t, is equal to 5. Remember that it is 5 multiplied by step function. 5, when we take the Laplace transform of a step function, we get 1 over s. So it will be 5 over s plus 5 multiplied this thing, s plus 4, s plus 2 square. And actually, it's not plus, it's minus. So in this example, I like to solve a slightly trickier function. So we have to take the Laplace transform of a shifted step function. So usually our step function has a step at time point t equal to 0. But in a case of a shifted one, we have a shifted time point where it has a step, okay? So we have to be a little more cautious with that, and we will now see how we can account for it. So this thing is quite simple. It will be g of s equal to 1 over 5, just a regular over s square, minus 1 over 5, and now let's keep an eye on that. So a shift is a result of our Euler's number to the power of minus some constant multiplied by t. So if we follow that logic but just backwards, we will see that actually this thing is produced by Euler's number to the power of minus 10s multiplied by 1 over s squared. So this is quite simple, in fact, but it can get a little tricky. So this whole thing is equal to 1 over 1.5 in brackets 1 over s squared minus 10 Euler's number to the power of minus 10s over s squared. This is it. So if I were to draw a plot of this function g, then let's first draw our 1.5 t ut. So it looks something like this. Let's say this is 0.10, this is 0.15. If I were to draw our step function, it will look somewhat like this. But since the total g is just the difference of these two functions, their slope will kind of cancel each other out starting from this time point. So essentially what we will have as a result is the green line, where we just have a constant, our time point t equal to 10. So we might as well be interested in taking the inverse of the function f of s to see what was its representation in time domain. So in order to do that, we will first have to simplify f of s, and by that I mean that we have to decompose the fraction into partial little fractions. So for example, in this case, we can write s plus 3 over s squared plus 7s plus 10 as s plus 2, s plus 5. And as we know, this is true, right? So if we just multiply the numerator and denominator of this partial fraction by s plus 5 and this one by s plus 2, then we'll get essentially the same thing. And our goal right now is to identify what is a and what is b. So in that case, a s plus 5 plus b s plus 2 will be equal to s plus 3. So it will be just a set of linear equations, quite simple, and you will get a equal to 1 over 3 and b equal to 2 over 3. So now we know that our function f of s can be written as 1 over 3 s plus 2 plus 2 over 3 s plus 5. And in that case, taking the Laplace transform is much easier. So the inverse of this will be simply 1 over 3, the inverse Laplace transform of 1 over s plus 2, plus 2 over 3, the inverse of 1 over s plus 4. And this we know from the table is equal to 1 over 3 multiplied by Euler's number to the power of minus 2t plus 2 over 3 multiplied by the same thing, but just with minus 5t. So I hope that you find this video helpful.